All right, hello everybody. Welcome to the video that's going to be used to introduce the second online Physics 232 lab on hydraulic circuits. So here I'm on the course website again, and so let's just scroll down to the manuals for the online labs. This is the video for experiment number 2, which is hydraulic circuits, and so I'm just going to click on this manual and open it up. And so what we've got here is we're going to try to develop this analogy between electrical circuits, which you'd be familiar with from Physics 231, and what we're going to call hydraulic circuits. So this is the flow of, say, a fluid through a pipe due to some pressure difference and so on. And so the first thing that's important to consider is the analogs between electrical charge and a hydraulic quantity, current and hydraulic quantity, and voltage differences and an equivalent hydraulic quantity. So in an electrical circuit, a voltage difference will drive the flow of current. In a hydraulic circuit, it's going to be a pressure difference that drives volume flow rate of some fluid. So volume flow rate is a volume meters cubed per unit time, or seconds. And so if we think of electrical circuits again, current is the charge per unit time, and so Q is that charge. And so the equivalent of charge in a hydraulic circuit is the volume. And so I think these are important things to keep in mind. If I was working with an electrical circuit and I had a resistor and I wanted to calculate the resistance, what I would do is I'd measure the voltage across the resistor and divide by the current through it. And so R is delta V over I. For a hydraulic resistance, which is going to be, say, a long, narrow tube, the resistance of that tube is the pressure difference, delta P, divided by the volume flow rate, which we're going to call capital Q. And so that gives us a way of defining a hydraulic resistance. Going back to the electrical case, if we had a capacitor, then the voltage across well, let's see. How is capacitance defined? Capacitance is defined as C is equal to Q, the charge stored on the plates, divided by delta V, the voltage across the capacitor. So if I wanted to define a hydraulic capacitance, what I would do is I'd work with those analogous quantities. So the charge is going to be the volume. So how much volume is stored in our capacitor, how much volume of some fluid, and then I would divide by the pressure difference across that fluid that's being stored, and that would tell me the capacitance. For our hydraulic circuits, a capacitor is simply going to be a long tube, and so the tube is going to have a diameter that is large compared to the tubes we use as resistors, so it's not there to impede the flow of the fluid, but rather to store a certain volume of fluid. Okay, so there's really two setups to this experiment. In the videos, you're not going to see the full setup, so I'm just showing you some of the pictures of the complete setup. The first one is a large container of fluid, so it's just water. It has a bit of soap mixed in with it, and then it has food coloring it, so it dyes it green. And then at the bottom of the container, there's an outlet, and so it's a rubber stopper that has a narrow tube that's stuck through it, so the fluid can flow through that tube. So in this case, it flows through this tube. Which way does it go? I guess it goes like this. And then the tube has its outlet here, and so the fluid drips into a beaker that's on a scale. And so what we're going to do is we're going to watch the flow of the fluid through this narrow tube, and we're going to measure the mass of water that's collected as a function of time. So if you remember, what we wanted to do in order to find, say, the resistance of this tube is to take the pressure difference, which is determined by the height of the level of the water stored in this large vessel, which is, I think it's given to you somewhere in the manual, or possibly in the YouTube video. We'll look for it in the description of the YouTube video. And then what we need to know is the current, or the volume flow rate. So what we're actually going to measure is mass. If we divide by the density of water, we would know the volume. And so if we measure how the volume changes as a function of time and plot that, the slope of that line will be the current. And once you have that current, then you can go ahead and calculate the equivalent hydraulic resistance of this tube. So one of the things you're going to have to do is measure the volume collected in the beaker as a function of time. And you'll do that by actually measuring the mass and then dividing by density of water. Okay, so that's step one. Then in the next step, we have our hydraulic equivalent of an RC circuit. So we still have our long, narrow tube, which is our resistor. This time, the outlet of that resistor tube is not dumping liquid into a beaker, but it's storing it into a separate tube here, which has a larger diameter. So again, it's not a resistance, it's there to store fluid. And so this is our equivalent of a hydraulic capacitor here. And what you're going to do is you're going to measure the level of fluid stored in this hydraulic capacitor as a function of time. And so effectively what we're doing is we're watching this capacitor charge up. And it should charge with some characteristic time constant, and that time constant is going to be determined by the hydraulic capacitance times the hydraulic resistance. Okay, so those are really the two measurements you're going to make. The first in part one is the mass of water as a function of time being dumped into the beaker, and the second is the height of the fluid in this hydraulic capacitor as a function of time. Okay, and so you can read the manual for some details. Here's the pre-lab assignment and so on. Okay, so if we go back to the website, maybe we'll just spend a couple seconds just going over how you would go about collecting the data. So for part one, here's a set of videos. If you click on this, it actually takes you to a playlist that has 3 different videos. The videos are all showing the same basic effect. The only difference is the diameter of the resistor tube. So there's a small diameter tube, a medium diameter tube, and a large diameter tube. Okay, and so let's start with the large diameter tube. I'm just going to pause this for a second. And so the first thing that you're going to do is, you can see in this screenshot, you can see the beaker on the scale. The scale has been zeroed, and so the mass that we're going to measure is actually the mass of the water that gets dumped into this beaker. And so you don't have to watch these videos continuously. I'll play a little bit of it so you can see what's going to happen. So here we go. We're putting the end of the resistor tube into position. And so there's the start of the flow of the water. So if we want, we can move this back frame by frame. And so we can say that, you know, this, look at that. So you can actually watch the first drop as it goes in. Oops, so there we go. This starts at about 15 seconds. And so you might just want to jot that down. And so that's kind of your 0 in time. And then as you let it play, you see clearly the mass is obviously going to rise as a function of time. Like I said, you don't really need to watch this continuously. We could just collect, 12 to 15 points just by clicking through different parts of the video. And so you could say at 21 seconds, it's 4.6 grams. At 29 seconds, it's 11 grams. At 42 seconds, it's 20.2, then 37.6, 57.3. And so you can very quickly go through and get, say, 12 or 15 data points. Okay, there's 3 of those videos. What I'm going to do is I'm going to go to the small diameter tube, which is this one. And you can see there's a really dramatic difference in the volume flow rate or the current. And so here is one where you definitely don't want to just watch this straight through. It's a 30-minute video. You'll just go and click through and get masses at a bunch of different times. So 3.2 grams, 4.0 grams, 4.7, 5.4, 6.2, and so on. And so you can collect this data in, less than a minute. And so you're going to do that for all 3 videos. That means you're going to plot the mass, or after dividing by the density, the volume as a function of time, get the slope of that line, and you're going to get the volume flow rate or the hydraulic current for all 3 of these resistor tubes. Some information that you would need about this experimental setup is in the description of the video. So each of the 3 videos has its own description. And so what you can see is that the inner radius of the tube for this video is 0.28 millimeters. And the height of the fluid in the hydraulic battery, or the big, large container filled with the green fluid, the water with green dye, that height is 23.1 plus or minus 0.05 centimeters. And then one of the things you'll do in your pre-lab is determine how you can use that height difference to calculate the pressure difference, delta P. And so then when you know delta P, and once you've figured out the volume flow rate, you can take the ratio of those 2 things to get the hydraulic resistance. And so that's the objective for part 1 of the experiment. Okay, so then going back to the course website, there's a second set of videos for the RC circuits. Again, it's a series of 3 videos, and in fact, they all use the same capacitance they use the same tube for the capacitance, and they use the same resistance tubes that were used in part 1 of the experiment. So here, I'll start with the large diameter tube. Let me just pause this for a second. And so what we have here is a glass tube. That's our hydraulic capacitor. And behind it is a ruler. And so these are millimeter divisions. And you're going to measure the height of the fluid as a function of time. Okay, and so you can see this one starts up pretty quickly. And it fills up quickly, and then the rate that it fills gets slower and slower and slower. And so that's exactly like charging a capacitor. When you charge a capacitor in an electrical circuit, it initially charges very quickly, and then it really slows down. It's that exponential, it's an asymptotic approach to equilibrium. And so once again, you don't need to watch this video all the way through. For this one, you can. It's only a minute long, but you can also just pause it and then just click through and record the heights that you see. And so what this is, I don't know, 24.38 millimeters or something. Here's 24.6 millimeters, and so on. You can just go through it like that. Okay, and so that one's quite fast for the large diameter resistor, and here's the video for the small diameter resistor. And you can see it's, instead of being a minute long, it's an hour long, so it's 60 times longer. And we'll just wait for the fluid to start to bubble in. So you can start to see it come up a little bit. The 0 on the ruler is somewhere around here, so I might just wait until it reaches probably right about here. I might call that 0, or pretty close to it anyways, and I would just jot down that the 0 in time is 31 seconds in the YouTube timer. Okay, and then again, it's not necessary to watch this straight through. You would just try to scroll through and get about 15 data points at different times and write down the heights of the fluid in the capacitor. And then in the description of the video, again, you're given the inner radius of the tube that is being used as the resistor, and then you're given the height of the fluid in your hydraulic battery. Okay, and so that's everything. So you would collect that data for the 3 different RC circuit videos. Okay, so let's go back to the course website. What you'll ultimately need to do are a series of linear fits. You'll do 3 linear fits in part 1 to get the resistance of the resistor tubes, and you'll do 3 linear fits in part 2 of the experiment to get the charging time constant tau of the RC circuits. And so what I want to do is I want to use the rest of this introduction to show you how to do linear fits in a Jupyter notebook that's running Python. And you may already know how to do this, and so if you do, then that's fine. You don't need to watch this part. If you need a refresher, that's fine, or if it's brand new to you, then it'll be introduction. Again, what I'm basically going to do is I'm going to reproduce most of what's already in this example notebook. I'll just give some little narration over top of the notebook that as I develop it. Okay, and so I'm going to just do this using the UBC Jupyter Hub thing. So you log in. It'll ask for your CWL when you do this, but I'm already logged in, so it'll just open something up for me. Okay, and so I'm going to close this and we'll just start with a new one. All right, so the first thing I'm going to do is import some useful modules. So if you watched the video introducing the first online lab, you would have saw that some important modules for us are NumPy and matplotlib.pyplot, and we'll import that as PLT. Okay, so we will use another module to do the actual linear fits, but we'll import that one when we get there. Okay, so what I'm going to do is I'm going to enter some data as an array, and the data that I'm going to import is like a current through a resistor and a voltage across a resistor. So not very exciting data, but it's actually real data that was taken probably, in fact, as part of the Physics 231 lab. And so the way you would import it as an array is you could say your current, and so the current that I measured was an RMS current, and so I'll call it IRMS, is equal to NP, so we're using the NumPy module, dot array, and then it's round brackets and then square brackets inside there. And instead of typing out all of the individual measurements, I've got them typed out already. So I'm just going to copy them and paste them into here. Okay. And then what I'm going to do is I'm going to import, I'm going to create an array for the uncertainty or the error in this measured current. And so it has the same format. And again, I'm going to just copy and paste some values that I have on a screen that you can't see right now. Okay, and then the other thing we measured is a voltage. This voltage was measured as a peak-to-peak voltage on an oscilloscope. And so I'll call it V peak-to-peak. I should call it peak P to peak P, MP dot array, and I'll paste in those values that I had. So of course you'll have your own data for whatever fit you're doing, and so you just type in the correct values, and then the error in the peak to peak voltage. Okay, and so we'll paste that in here. And so it's good practice if you can to try to comment your work, and so maybe we'll just say enter in the experimental data. All right. So what we're going to do is we're ultimately going to make a plot of, say, current as a function of voltage, and we're going to use that to try to determine a resistance. Okay, so if we plot current as a function of voltage, then the slope of that is current over voltage, and so that should be the inverse of the resistance. So our plot should ultimately have the inverse of resistance as our uncertainty. Okay. So if we want to do that and get the right answer, I can't have a current measured in RMS and a voltage measured as a peak-to-peak voltage. So I have to have them in the same kind of units. And so what I'm going to do is I'm going to calculate an RMS voltage from the peak-to-peak voltage. And so that is going to be divided by 2 times, here's another NumPy function. They have a square root function, np dot square root. And so dividing by 2 converts our peak-to-peak voltage to an amplitude, and then dividing that amplitude by root 2 converts it to an RMS voltage. And then we have to do the same thing for the error in our voltage. We want the error in an RMS voltage, which is the error in the peak-to-peak voltage, divided by 2 times the square root of 2. Okay, and so let's say we're going to convert our voltages to RMS. Okay, good. The other thing I want to do is we're going to have a plot with a y-axis and an x-axis, obviously, and we've entered some error bars for both the x and y quantities. And so I just want to look at the size of the relative errors. And so what I'm going to do is I'm going to say that the relative uncertainty in the current is going to be the error in the current divided by the current. And, oh, sorry, I wanted to do just a regular enter, not a shift enter. And the relative error in the voltage is the error in the voltage divided by the voltage. And what I want to do is I want to just print the ratio of these two. So I want to print, I think, the ratio of the relative uncertainty in the current to the ratio of the relative uncertainty in the voltage. And if I do that, we can see we get a number of like 3, 2.5, 2, 3. This one is only 1.25. But in general, what we find is that the uncertainty in the current, or the percent uncertainty or relative uncertainty in the current, is at least a few times bigger than the typically a few times bigger than the relative uncertainty in the voltage. And so that means what we can do in our analysis is to probably neglect the uncertainty in the voltage, because the uncertainty in our experimental measurements seems like it's dominated by the uncertainty in the current. And so here we're going to examine the ratio of the relative uncertainties. Okay, and so we will find that the relative uncertainty in the current is larger than that of the voltage. So in our analysis going forward, we can neglect the uncertainty in the voltage data. Okay, and so we can put that on a new line. Okay, good. So with that, I think we can make a plot of the data. So I want to make a plot of current versus voltage, and I want to have the error bar shown on the current data. So we haven't used this yet, at least in the first video. Matplotlib has a function called error bar. And so it's PLT to get that module, and then error bar is the function. And the format is the data that you want on your x-axis, comma, followed by the data for the y-axis, comma, followed by the uncertainty in the y data, which for us is the error in the IRMS. And so if we just run that, we get a plot. And so it's these little things here are the error bars, and it's not showing data points, it's just connecting the one point to the next one with a straight line. And so we could do some formatting to make that look better. So let's plot current versus voltage with error bars. Okay, so the first thing we can do to format our plot is we could do this FMT, which is format. And if we have a quotation mark, K will be give us black data points, and O is to actually give us little circular data points. And go Shift Enter. And so there it is. And so that looks nicer. Although the error bars are there, we can't see them because now they're covered by our data points, so we can do a little bit more formatting. Before we do that, let me just point out that when we were doing the other scatter plot without error bars in the first video for experiment 1, we were just using plt.plot, and in that case the format wouldn't be there. So there's for some reason some odd difference between the notation used for plt.plot and plt.errorbar. Anyway, so we need I think we need the FMT in this version. Okay, so we can do some other things. We could do, say, marker size is equal to 5, and if we do that, that makes our little points a little bit smaller. And then we can add a bunch more things in there. I'm going to start putting them on a new line, and you could just use a slash to start a new line, and then we could say something like line width is equal to, I think I have 1.8, and then we could put something like marker edge color, and so we can set that to be whatever we want. I'm going to use blue, and then we can do a marker face color, and we could do whatever we want. I'm going to use yellow, and so we'll probably do one more option, but let's just see what all this looks like. And so there we go. The line width is the width of the line used to draw the circle. The inside, it's hard to tell, but it's colored yellow, and the line that's been drawn is blue. The error bars still aren't very prominent, so we can do, oh, in fact, I guess you may not even need that slash, but I don't think it hurts to have it. So to make the error bars a little more prominent, we could put cap size, put in an option for cap size. And so it's going to put these little horizontal lines at the ends of the error bars. And so then now at least we can see the size of the error bar, say, relative to the point size and so on. Okay, just to finish this off, we could do plot x label, and we can call it whatever we want. So the x is the RMS voltage in units of volts. And we have y label, and so that is RMS current, say in amps. And so that should work. Okay, notice that when I do that, the Jupyter Notebook puts like some text here related to this last line that I wrote. So if I want to suppress that, I could just put a semicolon, and then we get only our plot. Okay, so anyways, that's just plotting, entering data, and doing the plot. What we would like to do is to actually start the linear fit. So now we attempt to fit the data to a straight line. Okay, we're going to have to import a module, so we're going to use what's called the, I think, what's it called? Yeah, we're going to use the SciPy module. So let's import it. So it's going to be import, and then it's going to be SciPy, and we're going to use optimize from SciPy. Actually, I've got the format a little bit wrong. This one's a little bit different. I don't know too much why, but from SciPy optimize, we're going to import curve fit. So I think what this format is actually doing is it's saying, you know what, this is from the SciPy module. We're not going to use very much from the SciPy module. We're just going to use this one thing called curve fit, and so let's just import that one single function. So anyways, we did it. Okay, so here's perhaps the trickiest part of doing this straight line fit is we have to define a function that we're going to fit to our data. And so this is a little bit inconvenient for a straight line fit because that's such a simple function. However, the advantage is if we learn how to do this for a linear fit, then we can use the exact same syntax and all the same coding for a fit to any kind of complicated model that we want. All we're going to have to do is we're going to just have to modify this function that we're about to write down. And so the format or the notation syntax that we have to follow is DEF for define. And then we can give our function any name we want. I'm going to call it a linear function. And we're going to have to pass our function some parameters. We're going to pass it some x values, so I'll call that x. And then we're going to have a slope and an intercept. Okay, and then the notation is a colon at the end, and when we hit enter, notice that it automatically indents the cursor. So everything that follows this define, whatever your function is, everything that follows that's indented is part of this function. And all we're going to do is we're going to say y is equal to slope times whatever the x data is plus the intercept. And so we're just defining a straight line. This is the part where, you know, if you were doing a polynomial fit, like to a quadratic or something, you might change this to like x and then here. So if, just to give an example, if we were fitting to a quadratic function, what we might do is instead define this to be a times x squared plus b times x plus c or something like that. Okay, so you can make your function whatever you want. It could be a sine function with an amplitude and a frequency and a phase or whatever. But let's just go back to our slope and intercept. And so our y is going to be slope times x plus intercept. And that's everything. And our function is going to return for us a value of y. So basically what's going to happen is we're going to pass some x values. The curve fit thing that we're going to use is going to adjust the value of the slope and intercept so that the calculated values of y match as closely as possible the measured values of y. What it really does is it looks at the difference between the measured value and the calculated value at each of these data points, squares them and adds them up, and it minimizes the sum of those squared differences. Okay, so anyways, that's our function defined. And so now we can actually implement the linear fit. So again, we're going to have the notation here. So now here's where we actually use the curve fit that we imported. And the options that we have to pass curve fit are the name of the function that we defined, the function that we're going to fit to our data. Then we have to pass it the x data, VRMS, and we have to pass it the y data, which is the current. This curve fit is going to return two things. One is the parameters. So maybe I can just call that parameters. So those are going to be our best fit parameters. And it's going to return another thing called the covariance matrix. And so I'll call that cov for covariance. And so let's just see what comes out when we do this. So let's have the outputs of params and covariance displayed here. So if we try this, there we go. So params is an array of two elements, and the two elements are the best fit value of the slope and the best fit value of the intercept. So they're in the order that we entered them here, so slope and intercept. And this covariance matrix is a 2x2 matrix, and we'll see in a second how we're going to use that. Okay, and just so you can see that, let's just do some format, some output. Just so you can see how you can do some of this stuff, we could do something like, say, print and say that the best fit slope is, and so then we would take our params, which is an array of two elements, and so the first element is our slope, and then we could say, and the best fit intercept is, and then we could, I think you can actually mix and match like single quotes and double quotes, so I don't think it really matters. I better be careful. Param has an S in it, and so the best fit intercept is this, and then I guess we could actually put a period maybe. I don't Okay, so it's not happy with something that I did. I have to close my bracket. Okay, good. And so what we should do is, let's see, the slope is rise over run, so we could give it some units. So it's amps per volt, and the intercept is at current, so it's in amps. Okay, and so there's how we can do this. Okay, so as you will see eventually in PHYS 232, the diagonals of the covariance matrix, which is the other output of curve fit, right, this COV here, the diagonal elements give the square of the uncertainty in the best fit parameters. So if we can select those diagonal elements and then take the square root, we'll know the uncertainty in our best fit parameters. And so let's see, we could say error in the slope is equal to, let's see, actually, first what I'm going to do is I'm going to say, let's just show something. There's actually, NumPy has a function called np.diag, and what that does is it selects the diagonal elements of our matrix. And so let's just see that. So here's our 2 by 2 matrix. The diagonal elements are 1.57 and 2.11. And so this output of this diagonal is 1.57 and 2.11. And so it has done what we wanted. And what I could say is I could take the first element of that array. That's the one, or in Python, I guess that's the 0, 0 element of this matrix. And so it's this one right here. And then if I take the second element of that array, it's the 1, 1 element of this matrix. Okay, and so then what I could say is that print the error in the slope is, and so it's going to actually be the square root of the first diagonal element, or the 0th diagonal element, and the, okay, and the slope is amps per volt, and the error in the intercept is np dot square root, and then it's np dot diagonal, and then that is of the covariance matrix, and we're going to take the element 1, and so I think I might have that right. We'll see. And then the intercept is a current. And so let's see what happens if we run this. So, okay, I got something wrong here. Oh, I keep forgetting to close my print statement. All right, good. And so we can check these things, and let's see, the slope is 4.5 times 10 to the minus 3, and the error in the slope is 10 to the minus 5, so that seems reasonable. The intercept is minus 3 plus or minus 1, so that seems that's plausible as well. Okay. The other thing we might want to do is we might want to plot our best fit line on top of the data that we have. Okay, to facilitate plotting the best fit line, we will use a NumPy function called, what's it called? It's called poly 1D to construct a polynomial with the correct coefficients. I'll show you how that's going to work. Okay, so the way poly 1D works is I'm gonna call this thing fit function, and I'm gonna take NP and then use this poly 1D, and what we're gonna pass it is that array of our best fit parameters. Remember that best fit parameters is right here actually. It's an array that has the slope and the intercept. And so what poly 1D is going to do is it's going to count the number of elements in this array to figure out the order of the polynomial. And so what it'll do for this case is it'll take the first one, the first coefficient, multiply it by x, and then x to the power 1 if you like, and then take the second coefficient and multiply it by x to the power 0. And so we'll get a linear line. X to the power 0 is just 1. If our params array had a third element, then poly 1D would construct a quadratic equation. If we had 4 elements in our params array, then poly 1D would construct a cubic equation. Okay, just to show you what it looks like, I think I can just get this thing to output the fit function. So probably what I want to, maybe I want to do this. If I print it, it might format it nicely. There it is. So what it did is it took this value, which was the slope, multiplied by x, and then added the intercept, which is a negative number, so it subtracted the intercept. Okay, good. So what we could do then is we could take fit function and we could pass it different values and evaluate this function for different values of x. We can evaluate fit function at different values of x via, I could just, all you have to do is take fit function and then pass it a value. If I pass x equals 0, we should just get the intercept back. We'll verify that. If I pass, let's see, x equals 1, then what we should get is, so if I go x equals 1, so that's like a voltage of 1, we should get something that's just above 0.004. And so let's see what happens if we do that. Right, and so this is feeding us the intercept back again, and this is something that's a little bit above 0.004. Yeah, so it's just subtracted a small amount, the intercept, off of this value. That's just telling us that the intercept is very close to 0, which it should be. If this was if this is Ohm's law, then V equals IR, the intercept should be small, and it indeed is. Okay, good. So this gives us a way to calculate the value of the best fit line at many different values of x. So I want to show you one thing. There's another nice function from NumPy, and it's called a range. And so the format or the syntax looks like this. So what we're going to do is we're going to say create a whole bunch of x values from -1 to +10 and make the step size 0.1. And so let me just show you what the output is. And so it's -1 to -0.9, -0.8, -0.7. So it's incrementing by 0.1 all the way up to 9.6, 9.7, 9.8, 9.9, and there would be 10 here. So I just picked I picked a range of values that was greater than a range of the voltages here. Okay, so then what I could do is I could say, well, what is the value of fit function at all of those different values of x? And so that's what it would look like. And now I could plot these versus x. So we could do plt.plot on the x-axis, give those x values from a range, and then evaluate the fit function, and we should get a straight line. And so there it is. Okay, and so what I want to do is I want to plot this straight line on top of the data that we already have. So I can just grab the plot that we already made. And so I can give a few other little notes here. So make a bunch of x values. And then here, let's reproduce the data plot, which I copied, I think. And I can probably get rid of the semicolon, not that it matters. And then we can add our best fit line. And let's see how all that goes. Good. It goes well, except for the fact that the best fit line, its range is way too big. So there's a couple ways that I could fix that. We could go back here and modify the x values so that they go from 0 to, I don't know, just over 2 or something. But there is another way to do that. And so we can adjust the, say, let's call it the plot window. And so the way we could do that is we can go plot, axis, and then it's actually 2 double brackets. And so the first thing we're going to do is specify the range of x values. And I think from 0 to 2.2 is good. And then the range of y values is something like 0 to 0.01. Something like that anyways. I put a semicolon there to suppress that output. And there we go. So there's our plot with our data and our best fit line with error bars on our experimental data. So that looks really nice. If we wanted to, we could save this plot as a PDF or whatever. Okay, so I'm almost done. I just want to do one more thing. Although we've made our plot with error bars, when we actually did our curve fit, like we never gave it any information about those error bars, and so it hasn't used the uncertainties in our measured data to, it hasn't taken that into account when finding the best fit line. What we would expect intuitively, I think, is that when points have a large error bar, they should have less importance or less weight in determining the best fit values for the slope and intercept when compared to points that have small error bars. A point that has a small error bar is one that we have a lot of confidence in, and it should play a bigger role in finding the slope and intercept of a best fit line, for example. So I want to redo all of this, but with a weighted fit. So everything we've done to this point has been an unweighted linear fit. To take into account the measurement uncertainties in the fit, we can make a relatively simple change to what was it, curve fit? Is it curve underscore fit? Is that the syntax? Yeah, it is. Okay, good. And so let's make that change. So a lot of this stuff we're going to be able to just copy from some of the things that we've already written. And so here, the first thing we'll do is put our curve fit. This is exactly what we had before. So all we need to do is to add one option. And that one option is sigma is equal to, sigma stands for uncertainty. And so we're just going to tell it what the uncertainty in our y measurements was for each of the data points, and it'll do a weighted fit. One thing that I'll mention is that some fitting routines in various programs, like say MATLAB, for example, it will ask you to put in the weights for the fit. And the weights are typically 1 over the square of the uncertainty. This curve fit is a little bit different. All it wants is the actual absolute uncertainties in your y data. And so that's why we're feeding it just the error in the RMS current. And so if we run this now, we should find that we get slightly different results because now this is a weighted fit versus an unweighted fit. So let's just confirm that. Previously, we had a slope of 4.56 and minus 3.03 for the intercept. So the slope hardly changed at all, but the intercept did change. Okay, and so at least that tells us that the weighted fit has at least changed the parameters somewhat. You know, the values of the error, the covariance matrix, 1.57 and 2.1 on the diagonals is, this is 8.7 times 10 to the minus 11 instead of 10 to the minus 10, and 3.11. So they did change the values of the diagonal elements of our error matrix or our covariance matrix. Okay, and then, so I think a lot of this we can just copy directly. And so here's our slope and intercept, and here is the uncertainty in those parameters. Okay, it's just the square root of those diagonal elements. And then we can reconstruct our fit function using the poly 1D. And so it has a different intercept here, so that's good. This stuff we don't need to copy, but we can copy all of this. And so we're going to make some x values. We're going to reproduce our data plot. We're going to add the best fit line, which now is slightly different, and we'll scale the axes. And there it is. This is a weighted linear fit to some experimental data with some error bars. Okay, good. So that's everything I wanted to show you. So I think a lot of the time when you're doing experiments, you run into these linear fits. And so this is a really useful thing to be able to do. And like I said, the real advantage of all of this is that now that we've done this for a straight line, we can easily make this function, like we'll call it something else, not a linear function, but some other type of function. And we could write whatever we want in here, any kind of nonlinear function with any number of parameters. And then once we've defined that function properly, all the rest of the fitting routine is exactly the same. So again, you would get your parameters would be output as an array. If you had, say, 4 fit parameters, for example, then your covariance matrix would be a 4x4 matrix, and the square roots of the diagonal elements would give you the uncertainty in those values. Okay. Good. So that's where I'm going to stop. Thank you very much, and we'll see you in class. Good luck with everything.